Okay, hi everyone. We're going to continue our discussion of types of reactions now with the redox reaction, which is also called oxidation reduction reaction. Okay, and in fact, that's what redox stand for. Is the first part of it is the reduction part, and the second part of it is oxidation part. Now, the key component of a redox reaction is that there is one of the reactants is going to transfer electrons and another reactant is going to accept that electron. Okay, and so that's one way you can recognize oxidation, reduction, or redox reaction. There's a transfer of electrons from one reactant to another. The way we can see it is given in this example between sodium and chlorine reacting to form sodium chloride. If you look in the periodic table, sodium has 11 electron, okay, sodium atom, that is, so neutral sodium, right? And chlorine, if you look at each chloride atom in the chlorine molecule here, each one of them should have 17 electron. And again, these are just taken from the periodic table. When you look at the number of protons there, the number of electrons have to equal the number of protons since we're dealing with neutral species. Now, NaCl, on the other hand, is an ionic compound. So in this case, the sodium and the chloride are ions instead of elements. So the question is, what is the number of electrons that is present in sodium ion? Well, sodium ion, remember, is Na+, so therefore it's lost one of those electrons, so now it only has 10 electrons. The chloride ion, it's written that way, so Cl minus, that means it's received an extra electron, so therefore now it has 18 electrons. So what you can see is that when we're looking between the reactant sodium and the product sodium, what has happened? We've lost one electron. Whereas we look at the reactant chlorine and the product chloride, here we have gained one electron. Okay, so that's the signature of a redox reaction. So an electron in this case has been transferred. It's been transferred from sodium to chlorine. Okay, so that's one way you can tell it. You can count the electrons and see that you have lost or gained an electron in the different molecular species that are involved. But the other way to tell is by realizing that these redox reactions are not double displacement reactions. So that's another way you can tell. Remember that double displacement reaction, they all have this pattern right here. AB plus CD goes to AD plus CB. So if the reactions doesn't look like that, then you know they're redox reactions. So you can, again, go back and look at that sodium, chlorine, going to sodium chloride reaction. Well, sodium doesn't really fit this pattern right here because this is supposed to be an ionic compound. Chlorine also doesn't fit this pattern right here, the CD pattern, because again, we're not talking about an ionic compound there with chlorine. Sodium chloride is an ionic compound, but it's only one of them. We need two on this side for a double displacement reaction. So again, that pattern of reaction doesn't fit double displacement. We would call it a redox reaction. Now we can take a look at this example right now and see which of these are redox reaction. Okay, I'm gonna do the first couple of them and we'll leave the other two for you to do. Let's take a look at this one right here. Again, easy way is to see, is it double displacement or not? So let's take a look. It's Mg, it's O2, and then it's forming MgO. Well, does it fit that pattern? AB plus CD goes to AD plus CB, which is two ionic compounds on the left, two ionic compounds on the right. This one doesn't fit, so this must be a redox reaction. What about this one right here, the second one? If you look at the second one, does it fit the ABCD pattern right there? Well, this one actually does. So HBr, that's your AB, because you can break that apart into H plus and Br minus. And then CaOH2, that's your CD, okay? Because you can break it into Ca2 plus, OH minus, so that's another ionic species that could be generated. What about H2O? Now that's kind of unique. People sometimes don't really realize, but of course H2O could be broken into H plus and OH minus. So that one actually is AD, and the last one is CB, and that is our Ca, and then Br minus. So you can see that that one actually fit that double displacement pattern, and so this one is not redox, okay? So not redox. But again, if you remember, when we talk about double displacement reaction, there's only two reactions that are double displacement reaction, right? There's this precipitation reaction where you get solid as a product, and there's also acid-base reaction. And remember, one of the ways you recognize acid-base reaction is when you have an acid reacting with a base, which is exactly what this is. So in other words, that's another way you can recognize that that's not redox, because that turns out to be an acid-base reaction, which is of course part of the double displacement reaction category. Okay, so we talked about double displacement in lecture before, and we talked about redox reaction just now. There's also another way you can classify reactions. So remember, our goal here in this chapter is really to learn some of the most common types of reaction that you see in chemistry. So we just talk about those double displacement and then the redox reaction. That's one way we can divide reactions into two major categories, right? Another way is we can divide it based on this pattern of how things combine together. To some extent, that double displacement reaction is also used here, but there's other ones that you'll see listed right here. So one of them is called synthesis or combination, and that means you're trying to combine two things or three things together to make just one thing. So that's the pattern right there, A plus B, so two different things becoming one compound right there. It could also be A plus B plus C goes to ABC. It could also be AB plus C goes to ABC. Okay, so there's many different ways you can do combination as long as you're starting from more stuff, going to fewer stuff. That's basically a combination reaction. Decomposition reaction is the opposite of combination. So now you're breaking things. You're starting from something that's contain multiple things, but all in one compound, and you're breaking it into multiple products here. So combination is you're combining things. Decomposition is you're breaking things. Here's a big category of reaction called single displacement. Almost sort of similar to double displacement, except that you're only displacing one ionic compound. So the pattern looks like this. You have A, which is an element, and then you have BC, and that's an ionic compound. And look at what happens here when you go to the product side. The A has basically kicked out the B, so the B now becomes single, so that's a new element. And then this guy is now partnered up. The C is partnered up with the A, so that becomes your new ionic compound. Okay, so you start with an element ionic compound, the cation kicks out the other cation. Now you got a new ionic compound and a new element as a result of it. That's what's called single displacement. And double displacement, which is the last one here, of course, is something you're familiar with. Now you have two ionic compounds, and then they're swapping the cations together to form these new ionic compounds in the product side. Okay. Now, since we already talked about double displacement, I'm not going to go in there too much or at all, really. What I'm going to do is spend time talking about the other three that are new to this section, which is combination reaction, decomposition reaction, and single displacement reaction. At the beginning, I just want you to be able to recognize this. You want to be able to see a reaction and know what the name of that reaction is. That's step number one. And later, we want you to be able to predict for single displacement reaction, what are the products that might come up. Okay, so let's take a look at combination reaction first. In this one, as I just said, simpler substances, so things that are simpler, combine together to form something that is a little bit more complex, so that contains more elements. Okay, there are several examples of this that you can see. So for example, a metal and non-metal can combine together to form an ionic compound. So that was the example we had before when we combined sodium and chlorine to form sodium chloride, but here's some other examples listed here. You have magnesium and oxygen. You burn magnesium basically and you form magnesium oxide. You can combine, in this case, CaO and CO2. So that might look to you like it's AB plus CD, but look, what is the product there when you get it? Well, it's just ABC, really. It's sort of a new compound right here. So everything, it's like you have two things combining into one thing. Okay, so that's a combination reaction. You can also have a metal oxide, and that could react with water. And when you do that, you can have a base. Okay, so what is a metal oxide? So metal oxide is basically a compound where you have a metallic element combining with oxygen. So for example, Na2O would be an example of a metal oxide. This one is actually incorrect, the formula, so I'm going to just cross that out. This should be the correct formula, Na2O. And then you add water to that, and what happens? Well, it turns out that they form a base. You might remember bases all have hydroxide in them, so when you combine Na2O with H2O, you end up getting NaOH. And then you can balance that equation correctly, using the method you learned in class on how to balance equation, right? So this is a metal oxide, this is water, and this is a base, okay? Now, you can also have a non-metal oxide. So a non-metal oxide is an oxide of a non-metal element. So what is an example? Well, here's an example right there, SO3. So um, S is a non-metal, it's combined with oxygen, so that would be a non-metal oxide. When we add water to this, it forms an acid. Remember what acids have to have? They always have to have hydrogen, so it starts with hydrogen. And what you want to think about is just how do we combine these two things so that I get an acid out of it? Well, it's going to be H2SO4, which is your sulfuric acid in this case. Okay, so these three here are examples of how we can get combination reactions. We can get metal non-metal combining to form an ionic compound. We can get metal oxide with water combining to form a base. And we can get a non-metal oxide with water combining to form an acid. What about decomposition reaction? Here is the opposite of your combination reaction. So you take something that's complex and you break it down into simpler substances, okay? So you get a bunch of products as a result of it. Now, what are some examples of these? If you recall, one of the things that we talked about in the prior section on acid-base reaction are some of these unstable compounds. You remember these guys right here that I was mentioning to you before. I said that these guys would break apart to produce some gases, right? So we call it at that point gas evolution reaction. So for example, something like H2CO3 would break apart into H2O and CO2. H2SO3 would break apart into H2O and SO2. And NH4OH would break apart into NH3 and H2O. But the key here is that breaking apart. Everything starts from one thing, but then it breaks apart. They decompose, in other words. So those are all examples of decomposition reaction. Okay, you start with a compound and breaks apart into two or more products. Okay, um, anything that's the reverse of these combination reaction that we just talked about, right? The reverse of all of these reactions. In other words, if you imagine something like this going the other way, or something like this going the other way, or something like this going the other way, that's all decomposition. Now, how do we make them go the other way? Usually by heating. So heating is a key component of a lot of decomposition reaction. Anytime you heat something, there's a chance that that compound will decompose, okay, meaning that it will break apart into two or more pieces, okay? And so here's an example. This is calcium carbonate, and now if we heat it, we can break it apart into calcium oxide and carbon dioxide. Notice that that's just the reverse of this reaction right here, okay? So we just sort of take it the opposite way. We can take an ionic compound and then heat it, and we should get an element plus oxygen. Here's an example, mercury oxide, and then we heat it up, and then we get mercury, and then we get oxygen. And that's really just the reverse of this first reaction right here, right? When you take an ionic compound and you heat it, then it becomes metal and non-metal element as a result of it, okay? And the last one, again, it's basically just the reverse of this reaction right here, the metal oxide plus water reaction forming a base. You can see that we start with a base here because it has hydroxide on it, and it breaks apart into two things here. One is a metal oxide, and then the other one is water, okay? All right, and of course the last one is we can, again, start with a compound here we call chlorides. Chlorides are anything that has ClO3 in it. And so this one is potassium chloride. If you heat it up, it will break apart into potassium chloride and oxygen. So now we're going to go into this third type of reaction that we call single displacement reactions. And remember that this particular one has a pattern that looks like this. A plus BC goes to AC plus B. And keep in mind that when we write something as A, that means that's an element. And then something like BC here would be an ionic compound. And then you're producing a new ionic compound and a new element. But the key pattern that you should recognize in the single displacement reaction is that the element knocks out the cation that originally is there, replacing it. And so now that element becomes the new cation, and then the cation that gets kicked out becomes a new element. And so that's why it's called single displacement, because you only displace or replace a single cation. Now, one of the most important things to know how to use to predict single displacement reaction products is something called the activity series. Okay. And the activity series is just something that tells you which element is more active than another one. So the activity is ranked from the most active at the top to the least active at the bottom, as you can see in that table, right? So most active right here, least active right here. Now, what does activity mean in this case? Well, it means that if something is more active than another element, it will be able to displace that element in the form of a cation. So for example, for this reaction here to happen, A plus BC goes to AC plus B, A must be more active than B, okay? Now, if you, on the other hand, run a reaction that looks like this, let's say called C plus DE, and you don't get anything. So we write an R here to indicate that there's no reaction. So if you do it that way and you don't get a reaction, that tells you that C is less active than D. Okay, so notice that the things we're comparing is the element and the cation. So same here, element and the cation. And we're trying to compare the two in the form of an element to see how active they are relative to each other. So this activity series that's shown here on this table is really helpful to predict what's going to happen when you mix two things together. Will there be a reaction or will there not be a reaction? Let's take a couple of examples down here, and then I'm going to go back to the previous one. Okay, so say I have this particular reaction right here, Cu plus AlBr3. Will there be a reaction or will there not be a reaction? And so what I need to do is just take a look at the position of Cu, remember, versus the cation, which is Al here. I want to see where they're located relative to each other in the activity series. So let's take a look right here. Here's the activity series. Cu is down here. Al is up here. Okay, now remember what we said earlier. For the element to be able to knock out or to displace the cation, the element has to be more active. In this case, Cu is down here. Cu is the element. Al is the cation. So Cu is actually less active because Cu is less active than Al. Then it's not going to be able to displace Al. And so when you mix Cu with AlBr3, you end up not getting the reaction. So we just write Nr on the product side. Now let's take a look at another problem, which is nickel plus AlCl3. So we're going to go back to our activity series, looking for nickel and Al. And we see that nickel is a little bit there in the middle. And of course, aluminum we had found earlier to be at the top. So nickel, therefore, is less active than Al. So again, we're going to have to write Nr and the product side because nickel is not able to displace aluminum. There's that one more problem there at the bottom for H. I want you to predict what happens there on the product side using the activity series. So now I want to go back and take a look at a particular situation with single displacement reaction when hydrogen is involved, okay? So keep in mind that the elemental form of hydrogen is H2, as you may remember, right? It's H2 gas. And so when we're trying to compare the activity of hydrogen to a metal, for example, we're going to try to see whether H2 is more active or whether the metal is more active. Now, the ion form of H is H plus, right? So remember that the reason I care about the ion form in this case is because in single displacement reaction, one of those elements is found in the form of the cation, and the other element is found in the form of its element itself, right? So that's why we need to know both how the hydrogen element looks like as an ion and as a free element, okay? Now, the only problem here is it turns out that that cation form of H can be found in two different compounds. And it could be found in acid, as we know it's kind of H anything, right? HX, for example, in aqueous. So that X could be Cl, could be Br, could be anything. And then it could also be found in water. It gets a little bit more complex than that too, because the water itself could be either in the liquid form or in the gas form. So the liquid form is lower temperature, the gas form is higher temperature. Okay? So in other words, just to kind of put everything in context here, for H, when you're trying to compare activity, there's three different forms that you have to worry about. Is the H in the form of an acid? Is it in the form of liquid water? Or is it in the form of gas water? Depending on which of those forms of H is found, the activity changes. Okay? And so the activity series will allow you to figure this out, but you just have to know how to use it. And so let's take a look right here. So this elements at the bottom here, they're all below H. So H is located right here. So all of those elements I just highlighted in yellow are all below H. So they're all less active than H. So they don't react with H in any form at all, okay? No form of hydrogen will be able to react with those elements below hydrogen, below H, okay? Now, what about the elements above H? Now, these guys, we're gonna have to worry a little bit. We're gonna have to kind of figure out who's gonna react with what, okay? First off, all of them is gonna react with the acid form of H, okay? All of them. So all the way from potassium at the top to lead at the bottom, all of them is going to react with HCl or HBr or any H that is in the form of an acid. Only these ones will react with water in the gas form, okay? So notice that those four elements at the bottom, iron, nickel, tin, and lead, those are not going to react with water in the gas form. Only the top part of the series is going to react with water in the gas form. And lastly, only the top three will react with water in the liquid form. So the water in the liquid form is the least reactive of all of them, of all of these form of hydrogen. So only those really, really active elements at the top will be able to react with water in the liquid form. Okay? But then you combine the top three plus the middle five, which is all the blue series right there, when reacting with gas water. And then all of them can react with acid form of water. But everything below H can't react with H at all. Okay? Now, let's apply this idea that we just learned to some of those other questions in the single displacement problem set here. Okay, so let's take a look. So here we have zinc, and then it's being reacted with gas water. Okay, so let's take a look at where zinc is on the activity series, and let's see where water is on the activity series. Okay, so zinc is here. Okay, so it's more active than H because H is down here, right? So that means it's going to react with some form of hydrogen. Now we just have to determine what kind of hydrogen form will zinc react with. Well, zinc will react with all the acids. It also will react with the gas water. okay, because it's part of that middle group of elements there. So that means that if I mix zinc with gas water, which is what the question is showing us, then I'm going to get a product. What would the product be? Well, this is all single displacement reaction follow this pattern. A plus BC goes to AC plus B. So what we need to do is just combine the cation form of H, remember that's H plus, and then what remains of water, if you take the H plus out, is you're left with the OH minus. So therefore here, the zinc is going to displace the H plus. The H plus is going to become an element. So the zinc is going to combine with the anion, which is hydroxide. So your product is going to be zinc hydroxide. And then you have to remember a little bit from standard charges that zinc has a charge of +2, hydroxide has a charge of -1. So the correct formula would be zinc OH2, okay? And then the other product is the element form of H, which, as we said earlier, is just H2 gas, okay? So you see the steps I went through there. I first determine whether there's a reaction or not. Once I determine the reaction, then I write the new ionic compound and I write the new element. All right, let's take a look at a second question right here. This is between mercury and nitric acid, HNO3. Okay, so then you see that that's an acid, so we're dealing with the acid form of hydrogen. So let's see where mercury is in the activity series. Well, it turns out mercury is all the way down here, and it's actually below H. And remember what I said earlier, everything that's below H doesn't react at all with H. Doesn't matter what form of H we're talking about. So in other words, in this case, we're not going to get any reaction. So we're going to write NR. Okay. There's three other examples here. This one, and this one, and this one right here, where we have a metal reacting with some type of hydrogen. I want you to apply your idea that you just learned about reaction with water and with hydrogen and with acid, and see if you can predict whether there's going to be a product or not. Again, if there's no product, you have to write NR. If there's a product, you're going to have to write the formula of the product. Now, this one right here is kind of interesting. The one at the bottom here with potassium and water, it doesn't give you any kind of state for the water. That's probably just a typo on my end. So just put this as liquid water, okay? And then you should be able to predict the products that come out on the other side. All right, now that we know how to predict the products for single displacement reaction, we're going to put all our knowledge together about those four reactions that we talk about: combination, decomposition, single displacement, and double displacement. And we're just going to be able to look at a reaction and determine whether it's one of those four, okay? So I'm going to take a look at a few examples here, and then you can do the rest of them. Let's take a look at the first one. It says Na2O plus H2O making NaOH. Well, the pattern here is I have two things and I get one thing, okay? So that could only mean combination, okay? And if you remember, one of the discussion was this is those metal oxide, that's what sodium oxide is, plus water, and that forms a base, okay? Let's take a look at the second one. The second one is BaNO3, 2, K2SO4 makes BaSO4 and KNO3. Well, all we have here are ionic compounds. Here's an ionic compound, here's another one, here's another one, here's another one. So it sure fits that double displacement reaction pattern where you have two ionic compounds, right? And they are combining together to form two new ionic compounds. Okay, let's take a look at, let's say, the third one right here, Al plus Fe2O3 forming Al2O3 plus Fe. That sure looks to me like single displacement, right? Element and an ionic compound makes an ionic compound and an element. So this one would be single displacement. And let's take a look at the fourth one. We got H2O2 going to H2O and O2. So that one we have a compound and then breaks apart into two products. Just the fact that I said it breaks apart tells you that that must be decomposition. Okay, so I want you to do the other four here. Afterwards, again, if you have any questions, you're not sure, feel free to check with me and I can answer your questions if you want to check your answer. All right.